Okay, so that's basically all we're doing on here. All right, so it tells us length of pregnancies are normally distributed with the mean of that and the standard deviation of that. Find the probability of pregnancy lasting longer than 309 days. Okay. So this first part, we know the value, we know 309. We're looking for probability. So are we going to use the dist or are we going to use the inverse? Yeah, you're going to use the dist. So make this bigger. So I've got equals norm dist. The number I care about is 309. The mean is 269. Standard deviation is 15. And from here on out in the class, that 0 or 1 on the end is always going to be a 1. So, all right. So the area to the left is 99%. What is the question asking us for? So like if I went back into the original question, what is this 99%? What would it mean? That would be the probability that the pregnancy was what? Well, it's almost 100%, but I mean, what is it the probability of? 309 days or less. Yeah, remember this thing always gives us the probability to the left, right? So I've got a 99% chance the pregnancy lasts less than 309. So the probability it lasts longer, which is what I want, what should I do? Yeah, 1 minus that guy. There we go.
Like, what's the order of the numbers that you did?
Okay.
The value and then the mean.
Let me pull this back up. If you don't remember, I don't know if y'all can see that there or not, but it actually tells you, whoops. It's, yeah, you can't read that little box. But if you ever don't remember, when you pull up Excel yourself, it tells you in this little box, so it's norm dist. First goes X, then the mean, then the standard deviation, then the cumulative, which the cumulative is the 0, 1 thing. So we did the value first, the 309, then we did the mean, which was 269, then 15, then the 1. All right. If the pregnancy is in the lowest 3%, so now it's the other way around. Now they're giving us the probability. Then the baby is premature. Find the length that separates premature babies from those who are not premature. So first of all, when we use normal inverse, we have to put in area to the left, right? Is that 3%? Is that area to the left or to the right, or what is it? Guess the other one. Yeah, it's to the left because it says, I mean, the length of the pregnancy is in the lowest 3%. So you're talking about the bottom. I mean, so it's 3% and down, right? So they gave us the one we actually need to use. So we're just going to put in norm inverse 3%. So norm inverse. And again, if you don't remember, it tells you, hey, first you put in the probability, which is 0.03. It says next you put in the mean, which is 269. And then it says next you put in the standard deviation, which is 15. So 240 days is premature, so, or 241. Let's do another one like that. All right. Human body temperatures are normally distributed with the mean of that and the standard deviation of that. Hospital uses 100.6 as the lowest temperature to be considered fever. what percentage of normal and healthy persons would be considered to have a fever? Does this suggest that the cutoff of 100.6 is appropriate? All right, so again, here we know the value we care about. We have 100.6. But now we want to know, hey, what's the probability? So we're using dist or inverse. Go back. So if you know a value and you want probability, use dist. And then the other way around, if you know the probability and you want to get the value, that's when you use inverse. And this one's just like the last one. It says that we want to find the percentage of people that are 106 and up, right? When we actually use the function, it'll give us 100.6 and down. So we'll do 1 minus the fever. But, all right. So we're going to go norm dist. We care about 106 or 100.6. The mean is 98.18. Standard deviation is 0.64. The last number is always a 1 from here on out. So this says 99.99% of people have temperatures, normal temperatures below 100.6. We want people above that. Yeah. Something very, very small. So that would be 2 decimal places. Well, it says percent, so I don't feel confident in moving the decimal twice on my own. So to 2 decimal places, this would be 0.01% of people. So does that seem like so if only 0.01% of people normally have 100-degree temperature, does it seem feasible to say, okay, anyone with 100-degree temperatures got a fever? Yeah, I mean, you're not going to make very many mistakes. So there's a very small probability a healthy person would be considered to have a fever. And physicians decide they want the minimum, bless you, they want to select a minimum temperature for requiring further medical tests. And we want to say, whoops, see if it comes back. While we're waiting for it to come back, I'll tell you what it says. It says, okay, it's back, never mind. It says we want to have 5% of healthy people misdiagnosed. Okay, so what are we going to do? So we know a probability and we're looking for a value. So what are we going to be using? The inverse, right? And what do we put into the inverse? Well, we always put in the area to the left. So if I'm trying to find the cutoff for the top 5%, what would that be if I did cutoff for the bottom? It would be cutoff for the bottom. What's the, if you're not in the top 5%, where are you? Yeah, the bottom 95. So I'm going to use inverse with 0.95. That'll give me, yeah, okay. So equals norm inverse. We're looking at the 95 percentile. Mean is 98.18. Standard deviation is 0.64. So we could consider people who have 99 degrees to have a fever, and we'd be okay. And 2 decimals, so 99.23. Let's skip ahead a little bit. So about 27. Okay, so this one you just kind of have to know the answer. So unbiased estimators, the definition is actually kind of technical. The only one that's biased out of the ones we know is standard deviation. So if you want to estimate the mean of a population, you take a sample, take the mean of the sample, and say, okay, this is an estimate. That's unbiased. Same thing, if you want to know the variance of a population, take the variance of a sample, that's actually unbiased. Believe it or not, if you want to know the standard deviation of the population and you take the standard deviation of a sample, you get a biased number. It's kind of weird, but so this is okay. Sample mean, that's okay. Sample range, there's no way that's okay. Sample proportion, that one's probably okay. I'm gonna say D. I'm not sure. Yeah. So range, well, I mean, there's no way you can expect your top and bottom in the population to be the top and bottom in the sample. So that one's going to be biased. Same thing, there's no way to really expect the mean in the whole thing, or the median in the whole thing. And then the standard deviation is the weird one. It's like, you would think it would be unbiased, but it's not. Okay, so now we're getting to the central limit theorem thing, which we said it last time, but we didn't actually do anything with it. So let me recap exactly what it says. So the central limit theorem let me actually restart my recording real quick.